Yep, we're good to go. All right, great. Uh, so, thank you, all of you, for being here on a Saturday afternoon. And afternoon seems like a strange time to be doing astronomy, right? What I'm going to do in this talk is I'm going to impress upon you the idea that astronomy is not just something that is done at night and through a telescope, but there are lots of other different ways also of doing astronomy and learning about the universe. Uh, Thanks to Shiva, first of all, and to the Chennai Astronomy Club for inviting me here to give this talk. And despite his best efforts, it got cloudy today. So we couldn't see the sun, but I will tell you a little bit about the sun later in the context of multi-messenger astronomy. So the question, I guess, to start with is what do we mean when we say multi-messenger astronomy? And to okay, so on Mac, does it automatically play things? Because I did not want that. This was supposed to be a game where I ask people to identify a song. We can use it. Excellent. Well, so now the cat is out of the bag. I'll tell you what I intended to do. You take any song, and if you split it up just into its different components, you don't really appreciate the full song, right? So this song, which now you've clearly identified which song it is, if I were to just play the drums, this is what it would sound like. Right? So if I just played these drums to you, could you identify what song it was? Probably not. In the same way, you could decide to just play the bass. And here's what that would sound like. It's extremely faint. You probably can't even hear it. I can barely hear it. I'm standing right here. So no. In the same way, you could listen to just the vocals, and of course, that tells you what the song is. And then you have to wait until, right? So this tells you a little bit more about the song, but still you don't really enjoy the song. You don't appreciate the song in its full glory. And something very similar happens in the context of astronomy. So far, for centuries, we've been doing astronomy by looking through a telescope, which means we are looking at light and just visible light. And just by doing that, we have managed to learn a lot about planets, stars, galaxies, and so on. But light is not the only thing that's coming to us. There are a lot of other particles that also come from these sources in outer space. So how do we collect information from all of these and get a complete picture of what's happening in outer space? So that is what we call multi-messenger astronomy. Right? And that's the thrust of this talk. Learning about the universe, not just using light, but using all of these different signals that are available to us. So to give you a brief overview of this lecture, I'll first tell you what these different languages are in which the universe is talking to us. Okay, and these are called different messengers, hence the name multi-messenger astronomy. I'll start off by telling you some of the open questions about the universe that we want to know. Why do we want to do astronomy at all? What are the things that we want to learn about outer space? And then we'll look at these different messenger particles. So we'll look at light, of course, because we do astronomy using light. But we also look at things called cosmic rays. We look at neutrinos. We look at gravitational waves. So I'll give you a little bit about all of these particles. And then in the end, we'll talk about a couple of so-called multi-messenger events. So things that we have actually seen in outer space from which we see light and we see cosmic rays and we see neutrinos and we see gravitational waves. So I'll tell you about some of these things, which hopefully will impress upon you the significance of doing multi-messenger astronomy. So let's start off with our messengers. The first messenger that we have, of course, is light, or what we refer to in physics as photons. These are light. We all know what light is. This is electrically neutral, travels in a straight line, comes to us from various different sources. We also have things called cosmic rays. Cosmic rays unlike light, are charged particles. So these are electrons, protons, charged ions, also things called muons, but these are relatively rare. So all of these charged particles are what we collectively call cosmic rays. So we also see cosmic rays coming from outer space. We also have a seat here if somebody wants to. Yeah, has that been figured out? He couldn't find the switch for it. Can't figure out exactly good without this answer, isn't it? Yeah. These lights, if you want to switch them on. Yeah, that's actually good. Yeah, this is better. Okay. Yeah, but if you can ask them to, yeah, because it's also quite distracting for everyone. See, that is the theme of this talk. We don't want light, we want other things. Is there a switch? Is there a switch outside by any chance? The flashing thing, we want that off. No, no, some. It seems like there's a combination of. That's okay. That's okay. Sushant, you are not on the solution. Yeah, let that be. Let me see Sushant. Yeah, turn on. No, not that. Yes, yeah. Now you are. Okay, great. All right, so that was about the cosmic rays. You sit here. That's okay. Are you locked? There are also a couple of seats at the back. Then we'll talk about neutrinos. And neutrinos are, again, neutral, electrically neutral particles. And they are very interesting, also personally for me, because that's the part that I work on. And then eventually we'll talk about gravitational waves, which had been predicted more than 100 years ago in Einstein's theory of relativity itself, but it took a long time for them to be actually discovered experimentally. So these are the four messenger particles that we're going to be talking about, and let's learn a little bit about them. But before that, the question is, what are the things about the universe that we want to learn? Why are we looking at these different messengers? So I have a set of 4 or 5 things that are interesting to me. Of course, there are lots of things in the universe that we don't understand. I'll just highlight a few of them which are of personal interest to me. So I'm putting them under light because it's part of the electromagnetic spectrum. So the first question is, how did the universe start? Okay, what was, yeah. What about gluons and Z bosons? So you don't see them from outer space. The Z bosons, we don't see them because they're unstable, so they will decay like before they come to Earth. Gluons are never found individually; they're always found within protons, so on. So those, as part of the cosmic rays, they will come, but not individually. So how did the universe begin? As per our current understanding, there was something called the Big Bang at the beginning, and then the universe has been expanding since then. The universe is something like 13 billion years old, so it has been expanding for that entire period. And we want to understand how the universe was right at the beginning. In the early stages of the universe, what was the evolution like? What were the processes that led to the universe becoming the way it is right now? Interestingly, when we look at objects far away in space, we are also simultaneously looking back in time. Because let's take an example. The sun, it takes around 8 minutes for light to reach us from the sun, which means when you're looking at the sun, you're looking at light which left the sun 8 minutes ago. So you're seeing the sun as it was 8 minutes ago. You're not seeing the sun as it was right now. Similarly, if you're looking at a galaxy which is, let's say, 1,000,000 light years away, that light left that galaxy 1,000,000 years ago. So you're seeing the galaxy now as it was 1,000,000 years ago. You're not seeing it as it is right now. So the farther away you look in space, the further back you're looking in time. It's kind of like time travel. In fact, right now, I am a few meters away from you. So light takes something like a nanosecond or something to get to you from me. So when you're looking at me right now, you're not seeing me the way I am right now. You're seeing me the way I was 1 nanosecond ago. So time travel. We're looking back in time every time we're doing astronomy. Another question is to do with mass extinctions in the Earth's history. Around 445 million years ago, there was this event called the late Ordovician mass extinction. A large number of species got killed off. This is not the one in which the dinosaurs died. That was around 65 million years ago. This is much before that. And one of the reasons given for this, one of the possible reasons, is that there was a beam of gamma rays, high intensity gamma rays that came from outer space and basically just fried all life on Earth. So question is, what are these events that can give rise to these intense gamma ray bursts, as we call them? Okay, so that's one more reason why we might want to do multi-messenger astronomy. The third question is the question of where atoms come from to begin with. We are made of carbon, hydrogen, oxygen, nitrogen. Our bones contain calcium, blood contains iron, and so on. Where did all of these atoms come from to begin with? Because right at the beginning, soon after the Big Bang, there was only hydrogen and some amount of helium in the universe. So how do the rest of these form? As per our current understanding, all of these atoms are formed inside a star. Okay, so a star is mostly hydrogen, which is burning up the hydrogen and converting it into helium in a process that we call nuclear fusion. So that's how hydrogen gets converted to helium. And then when the star runs out of helium, it will start fusing the helium and convert it into carbon. So this is the process by which stars shine. This is how they create light and heat. So it's a whole chain of elements that are formed, from hydrogen to helium to carbon to neon and so on. And so all of these atoms are there present inside a star. And then when the star dies, all of these atoms are released into the universe. And eventually, when some new planets are formed from all of that gas and dust, all of your carbon and oxygen and everything, which is now interspersed in space, will get captured by those planets. And that's how we have carbon on the Earth. That's how we have oxygen on the Earth, and so on. So as we like to say in astronomy, we are basically all children of the stars because we are all made of dust that was at some point billions of years ago inside a star. Okay, so we are all made of stardust. Now, this process works for elements up to iron. So all these elements up to iron, they are made inside a star while it's burning. Question is, what happens to the elements beyond that? Because there are lots of other elements also in the periodic table beyond iron, all of your gold and silver and lead and mercury and all of that. So where did that come from? To answer that question, we have to talk about how stars die. Now, in the year 1054 CE, there were records both in Europe and in China. Astronomers, actually not astronomers, common people as well, when they looked up in the sky, they found that there was a new star that had just started to shine. And it was so bright that for many weeks, you could even see it during the day, even when the sun was there. Now, this is something today that we understand, we call it a supernova. It was the explosion that accompanied the death of a star. And when these stars die, depending on how heavy the star is, it can either form something called a white dwarf or a neutron star or a black hole. The heaviest stars become black holes, and these are objects whose gravity is so strong that not even light can escape from them. Now, and it's in these explosions that happen when the stars die that you get these heavier elements that are produced. So all of your gold, silver, etc., these are produced in the death throes of stars. The process by which this occurs, stars becoming white dwarfs or neutron stars or black holes, this was discovered by a bunch of people, but these were two of the main people who did it. Does anyone know who they are? Okay, very good. So the one on the left is Chandrasekhar. That person? No, that is Oppenheimer, the same guy who made the bomb. He did a lot of work in astrophysics as well. So these were some of the people who figured out the process of the death of a star. All right, great. So let's talk about our messengers now one by one. So I'll talk a little bit about light, then cosmic rays, neutrinos, and eventually gravitational waves. Now, light, you may remember from your school days, is actually part of an entire thing called the electromagnetic spectrum. Okay? There's a very small part of the spectrum which our eyes are sensitive to. So this is the part from violet to red. And this is what we call visible light. It's a very small part. You can go to higher and higher wavelengths. So you'll come across infrared, you'll come across microwaves, you'll come across radio waves. So these are just light that has been sort of, you can think of it as stretched out, longer wavelengths. And in fact, radio waves can have wavelengths of the order of meters, kilometers even. Visible light has wavelength of around microns, okay, so less than human hair. You can even go to smaller and smaller wavelengths. So you can talk about ultraviolet light, you can talk about X-rays, you can talk about gamma rays. So the smaller the wavelength becomes, the more energetic and the more penetrative power these the light or the photons have. So there's no reason why we should stick to only visible light, which is what we used to do when we used to basically look through a telescope, peer through it. So we do nowadays astronomy also with infrared, with radio, with microwaves, with X-rays, gamma rays, and so on. So these are all different fields of astronomy in their own right. For the purpose of this talk, I'm just going to concentrate on one segment of this, and this is to do with microwaves. And there's a very interesting reason why I'm choosing microwaves. In the 50s, there was a lot of interest in studying radio waves and microwaves by telecommunication companies because we send signals, telephone signals, telegraph signals through these wavelengths. And so Bell Labs in New York, they were very invested in doing research on this. And they had found that there are sources of radio waves in outer space, for example, from the center of the galaxy. Now, there were these two guys, Penzias and Wilson. They had built this telescope, and this is a telescope not for visible light, which is why you can't see any glass or lenses or something. It's like a big box which collects radio waves from outer space. But they, in their signal, they were finding a constant hiss as a background. You know, the kind of thing where on the radio, if you're, as you shift between stations, you get like a faint hiss. That kind of thing they were hearing. And they couldn't identify the source of this background hiss, and they needed to get it out because they were trying to get clear signals. Now, one of the things they noticed that there was some white insulating material that had been deposited around this telescope of theirs. So they thought maybe that is the source of this. When they investigated what that white insulating material was, any guesses what it was? Yeah. So some pigeons had made a house inside that telescope, and they had deposited white insulating material, as the paper said. So they had to go and scrub it out. Then they tried to see whether there is some specific direction in which this hiss is coming from. So this is a telescope that you can move around, and you can see if there's more coming from the north, from the south, etc. You know, directionally, is there any kind of dependence? And there wasn't. It was the same in all directions. They tried to see if there was some kind of a variation with the time of day. Because if it's coming from the sun, for example, then maybe during the day you'll get more of it. At night you won't get enough. But no, it was constant throughout the day. 24 hours, exact same hiss throughout. They try to see if there was a seasonal variation. So as the earth goes around the sun, is there any change in this hiss? No. Perfectly constant, no matter where they pointed it, no matter what time it was. And there was only one conclusion, that this was coming from outer space, not just from outer space, it was coming from everywhere in the universe. At every point in the universe, there is this hiss, this kind of light or photons of a certain frequency that they're getting. And they went and showed this to some theorists to ask if the theoreticians have some idea of what this might be. And they said, yes, we actually have a theory which says that there should be this constant hiss, and we haven't been able to find it so far. And here, somehow, accidentally, you just found it for us. Turns out, this is something called the cosmic microwave background radiation. And this is the light that is left over from the Big Bang. which is why it is coming from everywhere in the universe. This is light that has a wavelength of around 2 millimeters. So, because the light from the Big Bang has been traveling for 13 billion years, as it has been traveling and space has been expanding, that light has got stretched out. So, all the light has become long enough to have a wavelength of around 2 millimeters. So, that's in the microwave region of the electromagnetic spectrum. And one of the cool, you wanted bad puns, one of the cool things that this tells us is that the universe is at a temperature of minus 270 degrees Celsius. So that's 3 degrees above absolute zero. That is the average temperature of the universe. And we get that by seeing the wavelength of this light, which is around 2 millimeters. And of course, we know that this background exists, and we know that this corroborates our theories about the Big Bang. But we are still constantly learning more and more about this, about the little variations in the background as you move around, to find out more and more finer details about what happened soon after the Big Bang. So I'll tell you now a little bit about that. That was about light. Of course, I could tell you more about radio astronomy, X-ray astronomy, etc. But for in the interest of time, I will move on from light to the next messenger, which is cosmic rays. And remember, these are charged particles that come from outer space. Now, these were discovered more than 100 years ago, 1912, when this guy called Victor Hess took some instruments in a hot air balloon and he took it up around 5 kilometers above the Earth's surface. And what he observed was that as he went higher and higher, there was more ionizing radiation which his instruments were seeing. So there were more charged particles that were hitting his instruments. So he concluded that there must be charged particles coming from outer space. And eventually we found that these are protons, electrons, ions, and so on. Now, these span a wide range of energies. We get cosmic rays from 10 to the power 6, which is 1 million electron volts, to 10 to the power 20, which is 100 billion electron volts. The electron volt is a unit of energy that we use in physics. It's basically 1 electron volt is how much energy an electron has if you move it over an electrical field of around 1 volt, over that much potential difference. So that is the energy which is 1 electron volt. This is something like a billion times smaller than most everyday energies that we have. So that's the scale we're looking at. Question is, how many of these cosmic rays come and hit the Earth for us to capture them and to study them? It turns out that the number of cosmic rays that come depends on the energy. So as you look at higher and higher energy, as you go to higher energy, the number of cosmic rays drops, and it drops quite drastically. So for example, if I'm looking at cosmic rays which have an energy of around 1 billion electron volt, then if I go out and if I make a square on the road which has a 1 square meter area, so 1 meter by 1 meter square, within that per second you will get 1 cosmic ray. Okay, so that's sort of the number or the frequency with which they come and hit the Earth. But if I talk about a higher energy, let's say I'm interested in cosmic rays which have an energy of around 1,000 trillion electron volts, then there are very few of them, because in that same square that we drew on the road, 1 meter by 1 meter square, I will only get 1 particle per year. So they've become much rarer. And if I want to go to even higher energy, so if I want to look at cosmic rays which have an energy of a billion trillion electron volts, then that 1 square meter is not enough. I need 1 square kilometer for me to get 1 particle per year. So this is very similar to taking a picture in a very dim setting. If you want to take a picture in a dim room, what do? You increase your aperture width so that more light comes in, and you increase your exposure time, again, so more light comes in. That's exactly what we're doing. Instead of 1 square meter, we've gone to 1 square kilometer, so it's like increasing your aperture. And instead of waiting for 1 second, we have to wait for years, and that's increasing your exposure time. Okay, so this is basically nothing but a cosmic camera. You're trying to capture cosmic rays, and you're optimizing to get as many of these cosmic rays as possible. So we have observatories that do this, and one of the biggest ones is the Pierre Auger Observatory in Argentina. And this is spread over some hundreds of 3,000 square kilometers. That is the total area of the observatory. And you can see that there are these little modules spread out over this wide area. So when a cosmic ray particle comes and it hits one of the atoms in the Earth's atmosphere, it creates a shower of particles. So a lot of secondary particles are formed. Some of those will also shower further. And eventually, all of the final particles will get observed by one of these different detector modules. And you collect all of that information and you use that to reconstruct what the original cosmic ray would have been like. So, what the energy was, which direction it came from, and so on. We also have similar cosmic ray detectors in India. So, there's MACE in Ladakh, and there's GRAPES 3 near Uti. And you can see GRAPES 3, the structure is quite similar to the one in Argentina. They have lots of small modules, and each of them, well, there are no pink particles coming from outer space. That is just an artist's depiction. But you have the shower of particles, and each of these little modules will capture individual final particles, and then you use that to reconstruct your original cosmic ray.
So you said the amount of particles that you detect per area is inversely proportional to energy, right? But shouldn't it be the other way? The more energy it comes, would be able to travel a lot distance and would be able to capture it.
So the kind of sources in the universe that can produce these particles, there are a lot of them that produce lower energy ones, and it's very few ones that produce very high energy particles. So that's the reason for it. Now, cosmic rays can also have some effect on our everyday lives. Have you, by any chance, recently come across an election with unexpected results? So, in 2003, there was an election in Belgium, and in this constituency called Schaerbeek, they found that one of the candidates. Okay, so let's go back. So they had electronic voting machines like we do, and they also had a separate like paper trail system of verifying those, like the VVPAT system that we have over here. And they found that this one particular candidate, she had, when they compared the number of votes that she had in the EVM versus in the VVPAT, she had 4,096 more votes in the EVM. So there was some kind of discrepancy between the two systems. But the hint that they had was that the difference is 4,096. And a lot of you are IT and software people over here. 4,096 is an exact power of 2. Now, the EVM, of course, is a digital machine, so it works on binary. You have zeros and ones. They found that the reason for this was that at the time of the election, a high energy cosmic ray had come and hit one of the EVMs, flipping one of the zeros into a 1. So it deposited some charge in the machine. One of the zeros became 1, which is why some extra 4,096 votes got deposited in this person's tally. So, well, strange things can happen because of. Well, they.
The re-election
Was it?
Yeah.
Oh, okay. I'm not aware of what happened after that. But okay. So this is cosmic rays. Who knows how many other elections have been affected by this? But so all other possibilities were eliminated, and this was the only one that was left. I mean, this is one of those things that you can't really reconstruct. It's how do you go back and check that there was a cosmic ray at the time? But this was there have so this is something called a single event upset, and similar things have also been proposed. Various other electronic machines also. I think there was one case where something strange happened in a video game, where somebody, I mean, I'm just making up an example. Like, like Mario has to jump a certain amount, and there's a limit to how much he can jump, right? But there was one particular event where one of the characters kind of like jumped a lot higher than they could, and they could never replicate that. And so one of the reasons for that was probably a cosmic ray event had come and done something at the time of playing this game. So if you do something fantastic in a video game, you can thank cosmic rays for that. Moving on to neutrinos, my favorite particles because I study them. And these are electrically neutral. And that is a big problem because electrically neutral particles are very hard to capture and to detect. And not only are they electrically neutral, they're also what we call weakly interacting. So if you if you want to detect something, it has to come and interact with your detector. But neutrinos are things which have a very, very, very small probability of interacting with matter. So neutrinos, first let me tell you what they are. These are produced in a bunch of processes. They are produced in the sun at the time of nuclear fusion. They are produced in just natural radioactive decay that occurs. They are produced in your nuclear reactors. They come from outer space. In fact, even our own bodies, they contain some small, naturally, our bodies contain some small trace amount of radioactive potassium, okay, potassium 40, and it's always just naturally present. Even food contains it. So even your own bodies, because you are slightly radioactive, produce something like 400 neutrinos per minute. So you yourself are a source of neutrinos. So there are a large number of these neutrinos that come from the sun, and because they don't interact much with matter, they just go through matter. So you can be standing over here and there are neutrinos coming from the sun. Trillions of them pass through your body every second. Have you ever felt any of them? No, because they hardly ever interact. All right. In fact, not just your body. These neutrinos that come from the sun, they pass through the entire Earth and they just go through, because even the entire Earth is not enough for them to interact. So very few, maybe one or two of them will interact, uh, but by and large, they just go through. So you can understand why they are really difficult to capture and study, because how are you going to get them in the first place, right? So one way of doing this is you build a really large detector. Because if you have a very large detector, so it has a lot of atoms inside the detector, so you are slightly increasing your chances of at least one of the neutrinos coming and interacting with the detector. So the larger the detector, the easier it is to capture a few neutrinos, which you will then be able to study. There's one more complication. Neutrinos come in three types. And as the neutrino travels, it keeps changing from one type to another. Now, let's say you've built a detector which is sensitive to one type of neutrino. But while it is traveling, if it changes to one of the other types while it is in your detector, well, then you're done for, because you will not see it. So neutrinos are very elusive. They avoid being detected. They will only interact if you have a very large detector. And they keep changing the behavior as they travel. We've all dated someone who looks like this. Now, fortunately, we physicists are very resilient and we have found ways to detect these neutrinos. So, here is an example of a neutrino detector. And you can see the size of this. This is basically a building. Okay, it's a tank of water which has a diameter of 39 meters and a height of 41 meters. So it's like a building full of water. And along the walls, we have little detectors. Okay, so these are called photomultiplier tubes. And you can see this picture of the inside of the detector while some maintenance work was going on. So it's a pool of water. There's a boat and there are technicians inside the boat. So that's the kind of scale that we are looking at. And they're doing maintenance work on these photomultiplier tubes. Eventually, the entire thing will be filled with water, and that becomes your neutrino detector. So this is the Super Kamiokande detector in Japan. What happens? How does this help us detect a neutrino? So when a neutrino comes through, it will hit one of the protons or neutrons inside the water, and very few of them will actually do this interaction, because most of them will just go through. Because this is very large, some of the neutrinos will manage to interact and they will produce a charged particle like an electron or a muon. Now that electron or the muon, as it is passing through this water, it will give out radiation, what we call Cherenkov radiation, and you will see that radiation on the walls, on those photomultiplier tubes, because they can detect light. So it's an indirect detection. You don't see the neutrino itself, but you see the secondary charged particle that the neutrino created. And these experiments, because the neutrinos, they, in spite of the detector being so big, there are so many neutrinos, but typically in a year you will see maybe something like a few hundred events, even though there are trillions and trillions and trillions of them coming from the sun, from the atmosphere, etc. So this is one of the detectors that we have for looking at neutrinos. What if I want to build a larger detector? Can you think of a larger tank of water? Yeah.
So about neutrinos, I have heard that all neutrinos are left-handed.
Yes.
Yeah, so are we certain that there are only left-handed neutrinos?
Okay, so to give context, in particle physics, uh, there is this property of any particle called chirality, which is sometimes also called handedness, and neutrinos are all left chiral or left-handed. To the best of our knowledge, yes, they are. To the best of our experimental knowledge, yes. There are some theories which say that you might also have a right-handed neutrino, but so far we have not found that in any of our experiments. But there are strong theoretical reasons for suspecting that there also might be a right-handed neutrino.
Because I have heard theories. I've heard a theory that dark matter might just be a right-handed
Could be,
neutrino.
could be. It's one of the leading theories of dark matter. But we don't know for sure yet. So I want a larger, yeah.
I might be completely off here, but isn't there something called the cosmic neutrino background as well?
Yes, but again, not detected. If you detect it, there is almost a guaranteed Nobel Prize over there. Uh, so yes, I want a large tank of water. Does anyone have a large tank of water? Ocean, very good. That is one possibility. Any other large tank of water you can think about? Antarctica, excellent. So we have built a detector in the ice at Antarctica, and not just in Antarctica, right at the south pole of the Earth. Unfortunately, no. It's not happening, unfortunately. Sorry. Okay. So this is a detector in Antarctica at the South Pole, uh, and it is very imaginatively called Ice Cube. So, uh, so here is this blue building that you can see. It is built exactly at the South Pole of the Earth. So this is the surface of the ice.
I was going to ask that.
Not the magnetic, the geographic South Pole. So this is where the axis about which the Earth rotates. And from the surface, there are these strings that have been put down into the ice, and the length of these strings are around 2.5 kilometers. Okay? And on each of these strings is a bunch of detectors. So similar to those photomultiplier tubes that were there on the walls of the tank, round detectors on this string, 17 meters apart, and those detectors are there from around 1.5 to 2.5 meters. So there's like a 1 kilometer long stretch of these strings which have detectors on them. Uh, does anyone know for reference what the height of the Eiffel Tower is? Yeah, 300 something meters. So if you put the Eiffel Tower over here, it will be this much. Okay, so that's the kind of depth under the ice that we're looking at. Very good. I'll come to that.
So what do you mean when you said strings?
String.
The actual fiber string.
What is mirror?
String. so because there are signals that have to come all the way up, it contains wires, etc., for transferring
You know,
signals.
like fiber optic cables.
Okay.
Yeah.
Basically, most of the instruments that we use in astronomy right now just use fiber optic cables for like long distances.
2 kilometers.
Yeah.
Yes. 2.5. Yes, actually, yeah. What was I going to say? Yes. No, but before that. Okay, yeah. So why are we doing this in the ice at the South Pole? The reason for that is that the ice in Antarctica, it has been that way for millions of years. It has got compressed. It is the most pristine ice that exists. It is pure. There are no impurities, uh, and well, until we put these detectors inside, but the ice is perfectly transparent. So any kind of light signal that goes through it, you see it perfectly. So that's one of the reasons for doing this over here. So coming back to the question of how we dug this and put it in, there's a very nice video that shows it. So first you make a little hole and then you send a tube inside that pumps hot water, and the hot water melts the ice. So they made this, and now something that pumps hot water into it goes through, and that makes it 2.5 kilometers deep. And then quickly, before it freezes in, you have to put your entire 2.5 kilometer long string with the instruments down. And then once it's down, done. It's locked over there. There's nothing you can do. You can't remove it, etc. If one of them stops functioning, and some of them have stopped functioning over the last 10, 15 years, too bad. It's stuck over there. You can't do anything about it anymore. So this is,
How far apart are the space?
if I remember correctly, around 125 meters or something. 125 meters apart. So in particle physics, all of these experiments that happen, these are large multinational efforts. So bunch of countries participate in this. India is one of them.
What is so interesting about neutrinos that we're spending so much?
What is not interesting about neutrinos? So
what are we trying to find? What are we trying to infer from neutrinos?
So, of course, I'll come to a bunch of the multi-messenger things that we want to know. But neutrinos are one of the most abundant particles in the universe after light. Yet they are, if you ask me, the least understood ones. So given how much of the energy of the universe is in neutrinos, and we still don't know about that. So it helps us complete our knowledge about particle physics and about the fundamental structure of the universe. So that's one of the reasons we want to study them.
What's the energy states of ice cube that it proves?
Ice cube, so ice cube in its original form, let's say 100 GeV onwards, but over the last 15 years or so, there's a smaller part of ice cube where they put more strings, because the smaller the spacing, the lower the energy that you can see. And so that's called deep core, and with deep core you can go down to around 10 GeV. And there are proposals to have something called the ice cube upgrade, which will allow you to even do 1 GeV neutrinos. So then you can start seeing a lot of atmospheric neutrinos, not just ultra high energy ones from outer space.
Would that be enough for like sterile neutrinos or like
Should be. So there are already bounds on sterile coming from deep core, not as good as the ones from shorter experiments, but yeah.
Why are the detectors kept at the depth of 1.5, 2.5, not just?
So in the atmosphere, you have a large number of muons being produced. Muons are also charged particles, but they can mimic the same signal that the neutrino has. So any kind of neutrino detector that you want to build it sufficiently underground, because the muons get stuck. Muons can't penetrate through, but neutrinos penetrate and go through. So it's to cut off the background of muons.
Also, when ice deposits over a period of thousands of millions of years, it is also the atmospheric air that would go and get compressed in the ice, like when the snow falls, the ice forms, and all that.
Okay.
So technically, isn't that not pure water? Because there definitely would be.
Would that not dissolve?
No.
Okay, then I'm not sure.
Okay, no, because you said pure water,
Right.
Pure water, so that's why I asked.
I see. So
I guess the thing is you don't need sterile water to do these.
it doesn't have to be sterile, but you should not have dust and other impurities which will scatter light. So there are no scatterers in there.
And the impurities from back then were not the man-made pollution impurities we have today, right? So whatever went in all those thousands of years ago and is now compressed that deep is way before when man existed and produced all of whatever we are doing today. So the kind of impurities we're talking about would have been of a very different nature.
It could be the suit from that 65 million years ago. And all that.
I mean,
Probably a foot down.
to put it very simply, whatever impurities you have, whatever size of the impurities you have, will not scatter whatever experiments these guys want to do in their energy scales. If you convert it into wavelengths, it doesn't matter.
So what does a neutrino event look like at ice cube? So here are all your strings, and when a neutrino comes through and produces a charged particle, and the charged particle will produce all of this light, and that light will illuminate some of those detectors on the various strings. So you will see something that looks like this. You'll see those different detectors having been lit up, and based on that you conclude what the energy of the neutrino was and what the direction was in which the neutrino came.
So the neutrino still passes through. It just interacts with the string while passing through. It's not that the neutrino stops.
It stops. So the neutrino stops. It produces the charged particle, and then it's the path of the charged particle that you see.
One neutrino will trigger several strings.
Yes. So it's the entire pattern which collectively tells you what the energy of the neutrino was and which direction it came from.
So you can kind of trace the path.
Yes.
And would we also trace the source, because it would most probably pass through anything?
Correct. So then you just look in that direction and you say that that was essentially that is the directional. But depending on the energy, the energy of the neutrino will decide what kind of resolution you get. So it might point to a relatively wide region of the sky. So you'll know it is coming from somewhere over there, but you might not know exactly what.
And then you can also go into like the fact of like the time scale itself of the reaction, of how fast it goes to the.
No, but these are traveling at almost the speed of light. So less than a microsecond.
You mentioned about types of neutrinos, right? Which type are you talking about?
So these are electron neutrinos and muon neutrinos. There's also a third type called tau neutrinos, which are a lot harder to detect. But IceCube has seen a few tau neutrino events as well, but not as many as electron and muon neutrinos.
These are the type of neutrinos that
they interconvert. Yeah. Somebody also said ocean. No, you want to build a detector in the ocean? Okay, we'll do it. There is the KM3 experiment, which has been built in the Mediterranean Sea off the coast of France. So in principle, it is very similar to IceCube. You have these strings with the detectors. Only thing is here, it's kind of attached to the base of the sea. And KM3 has also been collecting data. We see very high energy neutrinos coming from outer space. All right, so let's look at the first of our two multi-messenger events. And in order to do that, I'm going to take you to 1987, when there was a supernova explosion. And this supernova from 1987 was very innovatively named SN 1987A. Okay. Maybe I don't remember. So this was a supernova that happened something like 168,000 light years away. And so of course, right in the beginning, there were just 3 detectors at different places in the earth, which suddenly saw a sudden spike, a sudden increase in the number of neutrinos that were coming. And it was only later that we actually saw the light from the supernova. So the neutrinos first came and then the light. Why do you think that is? Because light is the fast. Light should travel faster, right?
I think the neutrinos would have mostly passed through a lot of the debris.
Fantastic, exactly. So at the time of the supernova, there's a lot of gas and dust and everything that comes out. Light slows down when it goes through a medium, like light through glass or through water. But neutrinos, because they don't interact, they just come straight through. So when you have a medium, light can actually travel slower than the neutrinos travel through it. So that's why the neutrinos got to us a few hours before the light got to us. And in fact, this time lag, knowing how much difference there was, gave us very useful information about how much dust and debris there is around the supernova. So here's an example of how looking at two messengers, light and neutrinos, gives us very valuable information about what is happening at the supernova. And eventually, a few months later, is when we also started seeing various things such as X-rays and cosmic rays, for example, coming from the debris and the clouds around the supernova. So once again, looking at various different messengers and the time lag between them told us about the process. How much is there so that the neutrinos can come come a few hours before the light? What is the spread of the debris? and what is the mechanism by which cosmic rays, gamma rays, etc., are being produced in that cloud. All of this is what we found out by looking at these messengers. We also got very useful information about the formation of those heavy atoms, which we wanted to find out about. How are these formed? So that's a process called nucleosynthesis. And studying the rate at which neutrinos and cosmic rays and light comes to us, we also find out information about the rate at which those heavier atoms are produced. We discovered that the supernova explosion, which is extremely energetic, there's only 1% of that energy which comes out in the form of light. 99% of the energy of a neutrino is emitted, of the supernova is emitted in the form of neutrinos. So this is where most of the energy comes from. So we found out a lot of these details about the dynamics of a supernova by studying the particles that come, the rate at which they come, and the time that they take to come to us. The last messenger that I will talk about is gravitational waves, and these were predicted quite early on. In 1916, Einstein wrote down his general theory of relativity, and from pretty early on, we have known that gravitational waves should exist, but they were first discovered only in 2016. So, what is a gravitational wave? If you think about regular waves like waves in water or sound waves or light waves, these are waves that travel through space. Gravitational waves are waves in space itself. It is not something traveling through space, it is the space itself which is wobbling. So, if a gravitational wave passes through us right now, the distances between us themselves will start to wobble. So, things will get close, things will get far. That is what a gravitational wave will do. It will change the structure of space itself. Okay? But they are extremely, extremely weak. These are produced only in the most energetic processes in the universe. For example, if you have two black holes or two neutron stars which are orbiting each other, and as they orbit each other, they change the structure of space around them. So you can see this is a simulation of two black holes, and as they orbit each other, they are sending out these gravitational waves. And as they get closer and closer and closer, you'll find that the frequency of gravitational waves increases. It's kind of trippy. Until they collide and they merge. And then after that, the gravitational waves will stop. So you'll see a lot of gravitational waves as they are swirling in towards each other, and eventually the gravitational waves stop. So this is a very clear signal that two black holes or two neutron stars have collided. They've spiraled around each other and then collided. But the size of the gravitational wave that comes is very small. These gravitational waves are very, very weak. I said space itself will change, right, when a gravitational wave passes through. How much will it change by? It will change by 1,000th the size of a proton. And we want to be able to detect that. So how are we going to detect such a small change in space? So the distance between you and me has to change by 1,000th of the size of a proton, and I have to detect that change. Now, there is this guy called Kip Thorne. Have you heard of Kip Thorne? Okay. Who is Kip Thorne?
Nolan's friend. Chris Nolan's friend.
Okay, excellent.
Theoretical physicist
Yes.
who also is he wrote for Interstellar.
Exactly. So he's a theoretical physicist who has done a lot of work in gravitational waves, and he was also part of Christopher Nolan's team when he was making Interstellar, because he wanted to find out how exactly a black hole looks, and he wanted it to look as realistic as possible. So he had Kip Thorne on the team who told him how the CGI effects should look based on actual physics calculations. So Kip Thorne had this idea for how to detect this very small change of 1,000th the size of a proton. And he said, let's use an idea called interference. Now, interference is something that we observe whenever there are waves. So here are some examples. For example, if you have water waves, so let's say you have a pond of water, and I have two places where I'm creating some disturbance. So there are ripples coming out. And so there are two separate waves, one from here, one from here. And as these two waves kind of hit each other, you'll find that there are some regions where the two waves reinforce each other. So you will get higher waves. But you'll also have some regions, like along this line and this line, where the two waves cancel each other out. So there the water becomes still. Okay, so this is called interference. You have constructive interference where the two waves reinforce and add up each other, and you have destructive interference where the two waves cancel each other out. You can also see the same thing in light. So if you have two sources of light, like two laser beams, or a laser beam that is passing through two narrow slits, so it's like two different sources, then the light from both of them will interfere, and you will see a pattern like this, where again you see regions where the light has reinforced and it's become brighter, but you'll also see regions where it has become darker, also between these. So that is constructive and destructive interference. You can see the same thing also with sound, and I'm going to do a little demo for you, and let us hope this works. May I use your phone?
Should work.
It should work. Let us see. Okay, so I have this app which generates a tone of constant frequency, and I have the same app on both of these. So let us first just get the volume right. So this is a frequency of 440 hertz I'm playing, okay, and this constant tone. Audible? Okay. Let us also do the same thing here and try and get the same volume. Yeah, roughly same volume. Okay. Now, on one of them, I'm going to keep it at 440. Well, no, first let's play both at 440. Okay. So these are both at 440, and there's nothing great about this. Now, one of them at 440 and one of them at 441. So slightly different frequency. 441. Okay. And now tell me what you hear. Do you hear something different? Good.
I'm not sure if I'm just hearing it just because you said it, but I think there's a slight flicker. We call it a tremolo effect.
Flicker, okay.
But I'm not sure.
Okay, wait, one is much louder than the other. Let us. Okay, this is the volume button. This is still a little louder. Why do you have such a good phone? Okay, I think these are both roughly the same frequency now.
Seems like the sound and the lights is too big.
Does it go up and down?
Yes.
Okay, very good. And what is the frequency of this up and down? Like how often is it going up and down?
Maybe half a second.
It's like
It is. So this was 440 and 441. Now let's do 440 and 442. And now you tell me what you hear.
The frequency is increased.
Is it happening? Is it happening faster than it was before?
Yes.
Okay. Should we try 440 and 443? And you know what to expect. Yeah. So
Sushant, before you, this is the first time I've ever experienced someone demonstrate interference with respect to sound.
okay.
I have heard the water thing. I've seen the water thing, but this is the
I
first
see.
time. Yeah.
So this is again the same phenomenon, interference, where you have at some places the two waves adding, and at some places the two waves cancelling each other out. So you can see interference with water, with light, with sound. So any wave interferes. And Kip Thorne says, why don't we use interference of light to try and detect these gravitational waves?
How do you capture the frequency of the resonating wave with respect to the two source waves?
So it is a difference. So when I do 440 and 441, then the up and down has a frequency of 1 per second. If 440 and 442, then it's twice per second. So in order to see interference of light, we use something called a Michelson interferometer. And let me explain to you what this is. So there's a source of light over here, typically a laser beam. This laser beam comes and hits a mirror. And this mirror is called a beam splitter. So this splits that beam of light into two, as the name suggests. We are very innovative. Physicists are very innovative at naming things. So beam splitter splits the beam. One of the two beams will move this way, one of them will move that way. And here we have two mirrors. So the light beams that have gone will reflect back from those two mirrors, come back, join at this beam splitter, and you will see the combined light on this screen. And depending on the distance of these two mirrors, you will see a certain kind of interference patterns. You will see a certain pattern of light and dark bands. Okay? And remember, it depends on the distance of these two mirrors from here. So how much distance has this light traveled? That's the important thing. Let's see a little animation.
This is similar to the Michelson-Morley experiment.
It is exactly that. It is the Michelson-Morley experiment. And so if those two mirrors were to move, then the interference pattern that you will see on the screen will change. Okay, so here's the same thing as a wave. It reflects back from the mirror and they combine, and you see what happens on the screen. You will see a certain kind of pattern. And so the point is, if a gravitational wave comes through and the positions of these two mirrors changes a little bit, it will change the interference pattern that you see on the screen. And that you can detect even for very small changes. But in order to do that, you need very long beams. You need your mirrors to be very far away. So here's an example of a gravitational wave detector in the US called LIGO. So the beam is somewhere over here, and these mirrors are 4 kilometers away. All right. So beam splitter, light goes there, comes back. In fact, the light actually makes multiple trips back and forth until you see interference on a screen. And when a gravitational wave comes through, those mirrors will move a little bit and you can see the change in your interference pattern. Now, there's a problem. Every time a truck goes past, everything vibrates a little bit. So that also affects your, in fact, forget the trucks. Like somebody walking past in this near the mirror will also trigger off this signal. So you can't do this with only one. You need to have one over here and one somewhere far away. So that if there is the exact same kind of vibration in both, then it has to come from a gravitational wave, because there is no truck which is going to trigger this and another detector which is a few thousand kilometers away. So anything of that sort, if you see a common signal in both of these, then it has to be from something like a gravitational wave. So we've done that, and we have, since 2016, we have been seeing gravitational waves. And in fact, now there's also LIGO India, which is being built in Maharashtra. So there's also going to be a gravitational wave detector in India.
Just out of curiosity, is there any other explanation other than gravitational waves for why there could be signals, or is it kind of direct evidence, or is it kind of inferred that that must be gravitational waves?
I would say it is direct, because we know when you have this in spiral of black holes or neutron stars, we know exactly what is the kind of wave pattern that we should expect. So that same thing has to be seen at both of these detectors. Anything else, first of all, will be only at one detector or the other, anything which is local. Plus, the pattern or the vibrations will be very different. It won't exactly match that, because it has to be a thing where there is a wave and it is increasing as the two are spiraling closer and closer together, and eventually it has to stop.
And that's what you see at both places.
Yes.
So it needs a cosmic event.
Sorry.
There has to be also a cosmic event happening.
So these are from cosmic events. These are gravitational waves coming from mergers of black holes and neutron stars.
So do you know which event led to each pattern that we detect?
So this is the event. You see this and you know that there was an event.
Somewhere in the past.
Until multi-messenger astronomy, because now that allows you to see that I also saw light coming from there, and that is what has triggered this.
One more question. You said the difference is 10 to the power minus 18.
Meter.
How do you measure that?
So
Because we need a scale to see that's 10 to the power minus 18, right?
So we know how this interferometer works, and we know what is the total distance that the light has traveled. So depending on the shift in the pattern that we see when a gravitational wave comes, we know how much it should have moved the mirror.
Sorry, so the same gravitational wave that came from these two neutron stars or black holes or whatever is being felt across the entirety of our planet. As in, there is like it's not like there are that wave can only travel in like a specific.
So it is not a directional thing. It's like a wave.
It's in all directions. It just spreads everywhere.
You could go to Saturn and you will see it over there.
As in the non-local counterpart to this observation center could be anywhere else literally anywhere else, and you would still technically be able to.
Yes, but so this is where having now. So I said there are two of them in the US. So this is where having multiple ones across the world helps, because then you can triangulate and find out exactly where it was. So that's why having multiple detectors is useful.
What these patterns look like?
The interference patterns of light, they will just look like bright, dark, and you the gravitational waves themselves. So it's the event is something called a chirp, and unfortunately I don't have a picture of it, but so think of a wave and then it gets faster and faster and faster, and then it just flattens out once the merger happens. So here is an example of something called a tidal disruption event, when you have, let's say, one black hole and one neutron star which have been orbiting each other, and black holes are very hungry. They want to swallow everything up. So the black hole basically shreds the neutron star, swallowing all of its material. And eventually, when they merge, you have a gamma ray burst. So you have light, you have, well, okay. So this is the neutron star, and then there's a companion black hole, which is slowly cannibalizing its twin. And when the two of them finally merge, when they combine, you see a massive burst of gamma rays. And of course, gravitational waves are continuously being emitted in the process. They have merged, and here is a beam of cosmic rays and gamma rays being emitted from it.
Are neutrinos also coming out at this point?
Neutrinos also are expected to come out. I don't think we have detected neutrinos from a black hole or a neutron star merger yet.
Black holes cannot emit anything because they are.
So these are not coming from the black hole. They come from the region surrounding the black hole, which is very energetic, because a lot of material that's falling in, and as it falls in, it's spiraling and it gets ionized. And so from the vicinity of the black hole, or what we call the accretion disk, there's a lot of radiation of all sorts coming out. That is what we can observe. We cannot directly see the black hole, as you pointed out.
There was something called like this temporary particle coming up and has oxygenated, and if the black hole absorbs one thing,
So the Hawking radiation. So these merger events are one likely source of gamma ray bursts, which might have at some point led to a mass extinction on Earth. So Once again, speaking of very innovative names, on the 17th of August 2017, we observed gravitational waves. So this event was called GW170817. And it was a merger of two neutron stars, some 144 million light years away. And this was the first time we saw two neutron stars merging. Before that, we had seen two black holes, or we had seen one black hole and one neutron star. This was the first time we saw two neutron stars merging. And that is very interesting because there are various nuclear physics effects that come into play only when there are two neutron stars that are merging. And so we managed to see gravitational waves from this event. And by the time, there had already been a system that had been set up which said that the moment some detector somewhere sees a gravitational wave, you immediately send off a signal to telescopes all around the world to look in that direction. And so we saw gravitational waves, and an alert was sent to astronomers all over the world saying, point your telescopes that side. And then 1.7 seconds later, gamma rays were discovered coming from that same direction.
Where were you?
I was a postdoc in Korea. So, and then eventually it took many hours or many days for X-rays and gamma rays, etc., to be seen after that.
What
So,
was that?
Hmm?
Why such a delay?
Why such a delay? Again, because of all of the material around the thing. So that slows light down. Plus, where is the light coming from? So some of it is emitted at the point of the merger itself. A lot of it also happens because of ionization, etc., which might take time. So hence the delay in various components of the light coming through. So here is a simulation of what that merger might have looked like. So of course you have gravitational waves, and then you also have a bunch of other kinds of radiation that are emitted. So by studying this event from which we saw gravitational waves and we saw various kinds of light come out, we got a confirmation that you can get gamma ray bursts when neutron stars merge. We managed to test Einstein's theory of relativity with regards to speed of light, with regards to gravitational wave emission, and so on. We also learned more about the mechanism by which heavier elements are formed. We found that there were 10 Earth masses worth of gold and platinum that were produced because of this collision. So that is where one wants to go if one likes precious metals. And we learned a lot of things about nuclear physics as well because neutron stars. So the last thing that I want to tell you about, and it's unfortunate that we couldn't see the sun today because this is related to the sun. We see the sun using light, visible light, and we have also looked at the sun using X-rays, using gamma rays, radio waves, and so on. But because the sun also produces neutrinos, you can also study the sun in neutrinos, or you can take a picture of the sun in neutrinos. But once again, because neutrinos are so weakly interacting, you need an exposure time of years. And after a decade or so of studying neutrinos from the sun, this is a picture of the sun that we managed to take. And you can see how pixelated it is. And the reason for that is that because there are very few neutrino events that we can see. So this is a picture of our sun in neutrinos. But here's the thing. Light that we see from the sun comes from the surface of the sun. That's what we see. But neutrinos are produced in the core of the sun. So this is not a picture of the surface of the sun. This is a picture of the core of the sun. And we can manage to take it because we have neutrinos at our disposal. With light, you could never see inside an astronomical object. With neutrinos, you can look inside an object. So I'll stop here with just saying that there are many different languages in which the universe has been talking to us. It's been talking to us in the language of visible light and X-rays and gamma rays and ultraviolet and radio, but also through the language of neutrinos and through the language of cosmic rays and through the language of gravitational waves. And it's only now that we are slowly starting to interact with the universe and understand all of these different languages that the universe is talking to us in. Thank you. If there are questions, I'm happy to answer.
So you said that neutrinos are the first thing that detect, and then there are a series of other things.
Usually.
Yeah. So, but how absolutely sure are we that neutrinos are the first thing that we get? There could be particles that we still not know, and that reaches first.
Yes.
Are we sure?
So speaking in the broadest terms of possibility, yes, there it is possible that there are some particles that we have not discovered yet, which might come first. Of the things that we know, we expect neutrinos to be among the first ones to get to us.
Did you say neutrinos have mass or are massless?
Neutrinos do have mass, very tiny mass. They are the lightest particles that have mass. They are at least 1 million times lighter than electrons. So extremely, extremely
So
light.
they can still be absorbed by black holes if it's not.
So a black hole,
It also absorbs wavelengths anyway. But
correct. So anything that has energy. So for example, even light, even though light is massless, light gets swallowed up by a black hole. Neutrinos as well.
What's your take on Havana syndrome?
What is that?
You don't know?
Okay.
It's a mysterious thing that happened in Cuba, in Havana,
Okay.
where people in the US embassy were reporting all sorts of physiological,
they were reporting loss of hearing.
all sorts of weird physiological symptoms.
Yeah,
People
cosmic
thought theorized it was microwave.
Cosmic rays.
Cosmic rays.
Yeah, that has to be.
Okay.
Elections.
Spies, man. Russian spies.
China or Russia,
Yeah.
one of the two.
You spoke of the event from 2017 and how a couple of seconds later we spotted gamma rays as well. So the intensity was nothing compared to whatever the extinction event is presumed to have had. Right? So
Yeah.
what are we talking about in terms of how close or how intense would that have had to be to decimate life?
So these gamma ray bursts, at least the ones that come from the mergers of neutron stars and black holes, these are very directional. So for example, you'll have a beam of them coming out back to back. Now, if we are unlucky enough and this beam is pointed at Earth, that's what leads to an extinction level event. But in general, you can have beams pointing in random directions.
So whatever we caught that day was the beam was going elsewhere. We just happened to catch some stray gamma rays.
Yeah. Otherwise, we would not be having this talk today.
Just wanted to check how fortunate or
very lucky.
Would pulsars be able to produce those kind of beams that kind of just destroy everything on Earth?
So I don't remember off the top of my head the energy range of light that comes from the pulsar, but we have seen a lot of So pulsars we see. So okay, the pulsars we've seen are sufficiently far away, and by definition, a pulsar is one which is pointing towards. So we are seeing this thing. So no, I mean, again, by virtue of the fact that we are here today, we have not seen a pulsar which fries us up.
But we can see the beams pointing.
Yeah.
We've just been lucky enough not none of them has pointed towards us.
No, they are pointing towards us, but they are far away enough that they are not intense enough.
And
Pulsars are radio waves.
Oh, those are radio frequencies. Okay, so they are also correct.
We use pulsars for everything. Anything from GPS satellites to your atomic clocks, they all use pulsars.
Okay.
Without pulsars, you can't really define a second at this point.
And the other question I had was that famous black hole picture that we had from some years ago. Was that just a simulation, or was that that wasn't actual light rays though? Is that what wavelengths did we see that on? That
So again, these are all coming from the accretion disk, which is around the black hole, and these come in various different wavelengths. So that was an actual quote unquote actual picture of a black hole, not a simulation.
The picture itself is
So connecting it
the
back
picture itself
to
is a
the image you showed of the sun's core.
Yeah.
So you said it's effectively a photograph but with neutrinos. Can you translate that to what that means when we know what a photograph with light is? What does that mean when it's with neutrinos? not able to wrap my head around it.
So what does it mean when we see a picture taken with light? You're seeing the parts where more light is coming from, you're seeing the parts where less light is coming from, and you're seeing the energy of the light because different colors, so different wavelengths. So same thing that we are seeing over there. You see which are the parts from where more neutrinos come. So the core will be brighter and the surrounding part will be less bright. And while that information is not in the picture that I showed, you also see the energy of the neutrinos.
From having either ice cube or that ocean, whatever, has gathered this information, or something like that has gathered this information and then put it together.
So not ice cube and the ocean, because those look at very high energy neutrinos, whereas the sun produces only a million electron volts energy neutrinos. So there are different detectors, similar in the sense that they are very large, but conceptually similar.
They would still be only tracking secondary particles, part of the secondary particle, all of those things, and then piecing this together, working backwards.
Yeah, just looking at a lower energy range.
What part of nucleosynthesis do you learn with neutrinos, or at least for the sun? Like,
from the solar neutrinos, I don't think we learn much about nucleosynthesis.
what do you learn then?
The fusion process itself.
Oh,
So
like
there are
whatever
various
happens in the core.
so there are various different fusion chains that occur. So there's something called the PEP chain, the boron chain,
Yeah,
etc.
yeah, yeah.
So all of these, we find out what is the rate at which each one occurs.
I see.
Neutrinos are particles or waves?
Particles, but within the broad framework of quantum mechanics, every particle is a wave. So you can also think of them as waves, and you in certain experiments or in certain contexts, it may be more useful to think of them as waves or as particles, depending on the kind of experiment that we're doing. But as I spoke about them right now, we were looking at them specifically as individual particles.
With that, we could able to find the source of the neutrino.
Yeah. So once again, if you have good directional resolution, you can tell where in the sky the neutrino came from. So you can tell the direction.
Just a question on your overall observation over the years. How closely astrophysicists and particle physicists actually work together? Because it seems like the largest scale and the smallest scale are actually intricately connected.
Right. And that connection comes through multi-messenger astronomy. So through multi-messenger astronomy is where the universe at very large scales and the universe at very small scales kind of come and talk to each other. It's a very upcoming sort of field of research.
Any thoughts on Lisa?
No. So there is a proposal. I don't know what the stage of funding, etc. is.
So the last time I spoke to the Lisa head, they told me because of the NASA funding, it's halted.
Okay.
But it's very likely that might be happening.
So I'll tell you what LISA is. The gravitational wave detector. So you have these two very long beams, 4 kilometers long on Earth. There's a proposal where, is there a marker or something I can? So this is the Earth. There is the Earth, and there is a proposal to have 3 satellites here, here, here. So these are going to be something like, if not even thousands, more than let's say tens of thousands or close to millions of kilometers. No, a million is too large.
No. Millions.
The moon is 300,000. So let's say tens of thousands of kilometers apart. 3 satellites. Think of them in a triangular configuration around the Earth, tens of thousands of kilometers apart from each other, and you're sending laser beams between them to detect gravitational waves. So a gravitational wave detector, but not ground-based, but in space, satellite-based. So that is a proposal called LISA, and it seems the funding has been halted. Let's see.
The thing is, they're saying it will come around 2035, very unlikely.
Okay.
And like the distance is like between each of the two dishes in the space will be around like 2.5 to 5 million kilometers, give or take. So it's like pretty huge baselines compared to 4 kilometers. They can like detect really faint.
So the longer the length becomes, you can detect smaller and smaller frequencies. So you get to see very different energies, etc., of these mergers.
But spacecraft.
Satellites.
No, spacecraft. They're not going to orbit the Earth.
Oh, they're not orbiting. Correct. Oh, yeah. In that sense, yes.
So it is 2.5 million. Each leg is 2.5 million.
2 million.
The
2.5 million kilometer per
The
second.
plan is, that's why I said spacecraft, not satellite. So
But this is beyond the moon then,
they
because
go.
oh, I see.
beyond.
I think this
Okay,
is an L2.
I see.
So yes, beyond.
Okay, yeah. L2 is on the other side, no?
Mm.
Any applications we are looking at by learning these waves? How do you apply?
So right now, no. And the reason for that is that we are still at that stage where we don't know enough about these in the first place. Once we know enough about them, one can try and apply them and get some kind of technological application. Think of this as like decades before we come to a point where we understand them and are able to control them enough to be able to use them for our purposes.
Actually, that's what I wanted to check. When you were saying that 99% of the energy of the supernova is in the neutrinos, and we don't have a way of, in any way, potentially harnessing or transferring or using the trillions of neutrinos that seem to be just chilling past us.
Yes.
So
If we could somehow harness the full energy of not even full, like even a small fraction of the energy of a supernova, that would be fantastic.
but from a neutrino to a form of energy that we know today, all of that is still pipe dream.
Right. Yeah. No.
What do you do now?
So I have a bunch of different things. Which one should I talk about? Okay, so Einstein's theory is of relativity is based on a property of the universe called Lorentz invariance. This basically means that the laws of physics remain the same no matter who the observer is, how the observer is moving. But so in one of the works that I'm doing right now, we are trying to test whether this is true at much higher energy scales and across large distances. So we are looking at these neutrino experiments which send a beam of neutrinos from one point and detect them like a few thousand kilometers away, and testing the predictions of this theory using the data from here. So that's one of the things I'm doing right now.
Is this different from what quantum physics says, which places the universe on the other?
So quantum physics by itself and relativity by itself were seen as separate, but around 50, no, I should stop thinking. This is 2026. So like 75, 80 years ago, these were unified in a common framework called quantum field theory. So this combines both quantum mechanics and relativity. So we all the particle physics that we do today is with a combination of both quantum physics and relativity. Yeah.
That's only for special relativity, right?
That is only special relativity. Excellent. General, we have not yet been able to combine with quantum physics.
What courses do you teach at Priya?
Generally, any physics course.
Do you think PhD is even possible with GR?
It has to be from a.
The other question.
It's just same statement as him. Do you even think
General
quantum
relativity
field
and
theory is possible with general relativity in the first place?
general relativity and quantum mechanics have to be compatible, because if they are not, then quantum mechanics will break down. And
Is it the right framework though? Maybe that's the question.
okay, so that one can ask, but there has to be a quantum version of gravity as well.
There has
That
to be,
is
but then maybe the framework we're using is not.
could be.
Is there a kind of layman's version of why general relativity and quantum don't see eye to eye?
I'm curious to see your answer now. This I want to know. This I really want to know.
Because I keep hearing about the quantum theory of gravity, but something that's kind of a dream of physicists, but why or why not?
Okay, I promise to come up with an accessible argument for this, and I can send it to you, and if you can share it on the WhatsApp group.
Out of syllabus.
Yeah. Okay. Do you remember what it's called?
I'm not sure. I don't trust the AI.
Okay. Sure. Okay.
String theory.
I don't remember it.
Are there any other questions? In that case, thank you, Dr. Sushant. It was one of the best talks I've ever seen.
Thank you. Glad you liked it.
Thanks for agreeing to give the talk. Thanks to all of you for coming here on a Saturday afternoon.
Thanks for making this happen.
Thank you.
So we'll do this every month. We already have a prospective speaker for the month end. So let's see what we can do. So can we all take a group photo? Is it also possible to connect this the other side of the city also?
What is the other side?
Somewhere in the OMR. Okay. So I'll tell you how the club operates. Right? So like I said, we are a not-profit organization. So we really don't want to charge people any money, but I mean, we have to do because we have to pay the venue. So this is actually a mutual friend's place. So he gives to us for kind of cheap compared to the other places. So that is actually the only reason why we stick to this place. So if I could find a place that is cheaper than that is cheaper than $200 per person, I'd be happy to move. Okay. And it also has to be a place that is family friendly. Yeah, I understand. Yeah, of course. So we can all take a group photo maybe this side. It's right to really good. I really like this. Like the way you presented it. The topic sounds technical, but